So in this video, we are going to learn about neural networks. We will differentiate between different clothing items like shoes, t-shirt, etc. By the end of this video, you will be able to build, compile, train, and use neural networks. We will also answer questions like how does the computer read images, how those images are transformed into the numbers, and what kind of pre-processing we need before feeding the images to the neural networks. So let's head over to my laptop. So we will start by importing bunch of libraries. We are importing TensorFlow, we are importing NumPy, Matplotlib, and we are just checking the version number of TensorFlow. So TensorFlow is a huge library, and we will be specifically focusing on the Keras module. So let's look at our dataset. Our dataset is of 70,000 examples of grayscale images in 10 categories. So by 10 categories, we mean we have categories of t-shirts, pants, sandals, handbags, boots, etc. And each image has a resolution of 28 by 28 pixels. Try to load our dataset. So we hit the load button. So this dataset is present in the Keras TensorFlow Keras module. So we don't have to upload it. We can just call it from the library. When we load this dataset, we will be loading into 4 arrays. We will be loading train images, train labels, test images, test labels. So if we look at the labels, we are provided with integers from 0 to 9, but we are also provided with the mapping against each label. 0 means t-shirt, 6 means a shirt, and 9 means an ankle boot. We have stored this list in class names. So let's try to explore our dataset a bit. As I mentioned earlier, that we have a total dataset of 70,000 images in 10 categories, and from those 70,000 images, 70,000 examples, we are going to use 60 examples for training and 10 examples for testing. And when we loaded this data set, and the TensorFlow already provided these data sets in these forms, because the data set was also already present in this form. So let's look at the shape of the train images. By shape, we mean since it's a matrix, it has 28 by 28 rows and 28 columns, and we have 60,000 example in train image dataset. If you look at the length of the train labels, for each example, we are provided with a label. And we can see that the labels are in this form, like they are in the form of integers. Similarly, we can look at the test images. We have 10,000 examples, and if we look at the test labels, we have 1,000 test labels. So here we are just looking at a train image, the first image from the train image dataset, and it's an ankle boot. Let's look at some other image. Let's say image number 5. What's the example number 5? It's like a t-shirt. So as you can see that the pixels are quite few. They are just 28 pixels in this direction, and 28 pixels in X direction, and 28 pixels in Y direction. Next, we need to pre-process our train and test images. It is important that we pre-process our train and test images the similar way, because if one image is scaled, one data set is scaled, for example, the training data set is scaled and test data set is not scaled, then we will not be getting the same results. So why do we need scaling? That you might be asking this question. So the reason behind this is both computational efficiency and mathematical reasons. We will cover this in a separate video. So currently, the data sets, each image is represented by a matrix of 28 by 28, and each array has a value from 0 to 255. So 255 is maximum, and if we want to scale it to 0 and 1, we will simply divide it by 255. As a result, all the images will be scaled to 0 to 1. So let's take a look at bunch of images from our data set. This part of data exploration is meant to check if we have correct data, high level, data quality check. We can see that the dress is labeled as dress, a sandal is labeled as sandal, and a coat is labeled as coat, and trousers is labeled as trouser, and so on and so forth. So this just to make sure that we are not training our neural network on wrong data set. Next, we are going to build our model. So when we say build our model, and if we are building neural networks, it means providing all the layers. So a simple way to look at the neural network is in the form of layers. There is an input layer, and then there are a bunch of layers in which computation happens. And then there is an output layer. So this neural network we are building has three layers. The one layer is simply the input layer and does the pre-processing. I will explain it in a minute. And there is in a dense layer, hidden layer, we also call it hidden layer. In this layer, all the computation happens. And this is the output layer. In this layer, the output is mapped to the categories we have. So we have 10 categories. When we will feed an image to this neural network, we will be getting answers like this image belongs to this category. So what is this 28 by 28? What we are trying to do in the first layer? In the first layer, we are simply flattening our 2D matrix. We have a matrix of the form 28 rows and 28 columns. What we are trying to do is to create a single vector of 784 pixels. This is the pre-processing we need. This is just a transformation, sort of a standard. That is why we need it, and for mathematical reasons, for performing linear algebra, we need this image in a single vector form. Another important thing to note is that we are building TensorFlow, Keras, and dot sequential. So what does this sequential does? So sequential is if we look at its documentation, so it is used for creating layers. When you are building a neural network, you are basically providing building different layers. If you have a very deep neural network, it will have many hidden layers. Right now we have a very simple neural network with just 128 neurons in between. You can change this number, but it will affect our accuracy and training time. For example, if we reduce the number of neurons from 128 to, let's say, 108, or maybe we reduce it to 20, we will get a different result. We will come back to this later. For now, we just keep it 120, 128. So we just build our model, and we have provided all the layers and stored them in the variable model. Next, we need to compile our model. So when we say compile the model, we mean specifying what kind of optimizer we are going to use, what kind of loss function we are going to use, how we are going to measure the accuracy, or what kind of metrics we are, how accurately the network is predicting. So we are using an accuracy matrix. Next, we move towards training our neural network. So again, we have stored our model and the variable model, and we are calling a method fit to it. I got an error because I did not compile my model. So let's run it again. So right now it is, as you can see, the accuracy of the model as it is seeing images, different examples, is improving. It started from 82% and getting to 88, 8, and we can see the curve is also flattening. Initially, the learning rate is pretty high from 82 to 86. Now we are getting from 89.04 to 89.6, and eventually we are after all the training, we have reached the accuracy of 91%. So if I go back and reduce the layers in my neural network from 128 to, let's say, just 18, and build my model again and compile it and just train it again, let's see what we are seeing over here. So we started with an accuracy of 80% and 84, 85, 86,
As you can see that the learning rate is not only slow, but we are not able to achieve the accuracy we achieved with more neurons. So how many neurons we need in a layer, how many layers do we need? This is a little bit of an art and depends upon the data set you are training. So for now, we just go with 128 again. Quickly train our model. And next we are going to evaluate the accuracy of the model. Good thing about TensorFlow is that it provides really comprehensive methods and saves us from the nitty-gritties of the coding, and we can focus our efforts on the valuable things. Here we simply call that evaluate method, and we provided the test images and test labels, and verbose 2 is basically just a formatting thing in what format we will get the output. So after this model is trained fully, now we can evaluate its accuracy. And we see that the model performed on test dataset of 10,000 images, it on average performed 88% accurately. This accuracy is lower than this 91% accuracy. What does it tell us? So it basically tells us the model is overfitted a little bit. When we say overfitted, it means that the model performs better on the training data set as compared to test data set. Let's make some predictions from our model. Now what we're going to do is to add another layer to our model. We are simply again calling keras.sequential, and we are providing it another layer. So before we have, our model has 3 layers. The first layer was the input layer in which we were flattening our model. The second layer was in which the actual computation was happening, and then third layer was the output layer. Now we are adding another layer which is simply converting the output to the probabilities. Why we are converting it to the probabilities? Because it's easier to understand in simple words. So we have added a softmax. What softmax layer does, it simply converts the output layer, which we call logit, to the probabilities. We have added it to our model, and now what we are going to do is, this is our model, updated model, and we are calling a predict method on it. What we are doing different from the evaluate method, here we are not providing it the test labels. Okay, now when we were evaluating our model, we provided it the test images and test labels so that we can calculate its test accuracy. The test images the model had not seen before. These are the images, 10,000 images we separated earlier. Now we are going to provide it the test images again and see how it predicts when we don't have provided it any label, sorry. So we are going to see how it is going to predict when we have not provided it any label. So here we stored over all the predictions in this prediction variable, and when we pick the first prediction by indexing it with 0, in this example we can see that the probability of the image belongs to 0.92 probability that the image belongs to label number 9 as compared to the label number 0, 1, 2, all they have a very small probabilities. We just simply run a max on this one, and we can see the maximum probability is on label 9, this one. And let's try to look at the label against this image. So we received this prediction for the first test image, and we are going to see over here what is the label against it. So when we run the label, we get that 9 again. So our model has predicted correctly. So this was the test on just one example. We can do it on multiple examples. Here we are defining some functions to test our model on multiple examples. Here we can see that most of the probabilities for label 9, and there is some probability that it is label 7. Similarly, we are picking another random number 12, let's say. Here we pick the first one. Next, we are going to predict 25 of our images, and we are going to see how it is performing in general. We can see that most of the time the model is pretty short, but we are looking at sometimes it is a little bit confused between like a zero, t-shirt and a coat. As you can see, they look like quite same, but still the probability is higher in for the label number 6. So that's about it. If you have to train some other neural network, it has given you the high level understanding of the how to train a neural network. All you will have to do is to change your data set, which we which we simply loaded from our TensorFlow. You will have to provide the data set over here, and then you will have to build your model accordingly. And let me show you the exact step. So here, if you are training on some different data images, so let's say you want to differentiate between a cucumber which is bent and a cucumber which is like straight, maybe. So what you need to do is, let's assume you are working on a big farm and you need to separate these different kind of vegetables so that they can be sold at different prices. So in that case, you will be simply updating your model according to the image resolution do you have with your on you. For example, if you have 720 by 720p resolution, you will update it accordingly. That will be a quite large image as compared to the one I have we just used in this example. Then you will decide how many layers do you need, and how many neurons do you need in each layer, and how many categories do you have on which you need to map your output. If you are trying to just differentiate between two, then you will provide two over here. So I hope this would be helpful to give you a high level understanding how to train a neural network for to differentiate between different images and do some classification. So hope to see you next video. Bye bye.